Welcome to the third lecture of this series where we will be covering description logics, which provides us the foundation of the Web Ontology Language, OWL. The outline of this lecture is shown here. We will be covering the limitations of RDFS, which leads us to a motivation for using or adopting the Web Ontology language. Now, that ontology language is based on description logics, providing the foundation of the Web Ontology language. And in order to better understand the Web Ontology language, I feel we should cover description logics in a little bit more detail. Now, what we will be covering are concepts, roles, and individuals, the difference between the open and closed role assumption, the unique name assumption, which is adopted in description logics, but not on the semantic web. And we will also be seeing interpretations and reasoning tasks, and we will see how we can reason using the Tableau algorithm. In the previous lecture, we've seen that we can use RDFS to model type and role hierarchies, and that we are able to declare the domains and ranges of properties. Now, RDFS is too weak to describe resources in sufficient detail. Examples include localized range and domain constraints. We cannot state that people can only have human children and elephants can only have elephant babies. We can't combine classes with union, intersection, and complement. And remember, this could have been useful for declaring that names belong to the domain of names are people or cats, which is not as easy to do with RDFS. We have no ways of declaring existence and cardinality constraint. We cannot state that all people um, must have a mother that is also a person, or that people have exactly two biological parents. And then furthermore, there's no way of indicating that roles or properties are transitive, inverse, symmetrical, and so forth. Now, we can introduce our own predicates in RDFS to declare that something is transitive, but there's no native reasoning support for that, and there's no standardized way in doing so. So if I were to share my RDFS vocabulary and I declared a property to be transitive using my own vocabulary, other people do not necessarily know how to interpret that. That's why we need standardized semantics and standardized reasoning support. So here's the example that I've alluded to in the previous slide. Assume that we want to model that dogs and cats can have names. Is the following RDFS correct? Well, here we have a property name that has two domain declarations, dog and cat, and its range is string. Is this correct? Well, it's not correct. Why not? Well, if something plays the role of having a name, then it's an instance of both dog and cat. In other words, multiple domain and range declarations act as a conjunction, not as a disjunction. So can we model something that represents dogs union cats in RDFS? That's possible using superclasses, something that represents dog or cat, and then both dog and cat subclass that let's call it an artificial class. And that may not be elegant depending on your domain, universal discourse, and may not be as scalable. And not only does OWL allow you to model classes in such a way, it also allows you to infer implicit information from explicit information, and it allows you to reason over your classes and instances. So why do we need reasoning? Well, reasoning allows us a couple of things. So it allows us to ensure that a knowledge base is meaningful. That means that all named classes can have instances. It allows us to ensure that a knowledge base is correct. So it captures the intuition of domain experts. And it ensures us that our knowledge base is minimally redundant. There are no unintended synonyms. And do pay attention to unintended because intended synonyms are fine. Reasoning also allows us to answer queries over ontology classes and instances. It allows us to figure out whether classes are more general or specific than other classes, and it even allows us to retrieve individuals or tuples matching a given query. Now, the Web Ontology language is an ontology language. Ontology languages should allow users to provide an explicit formal conceptualization of their shared universe of discourse. Now, OWL is such an ontology language, and moreover, it's a W3C recommendation, so it's a standard. The first one was published in 2004, and OWL 2 was published in 2012. The motivations for OWL was a well-defined syntax, formal semantics, and efficient reasoning support for the semantic web. Now, but before we cover OWL, we need to discover the logics that provide the formal foundation of OWL, and that is called description logics. So in this lecture, we will introduce description logics with the goal of better understanding some of OWL's aspects in the next lecture. Now, what are description logics? Well, description logics is a family of knowledge representation languages, and there are many of them, and they allow you to describe your domain or your universe of discourse in terms of concepts, roles, and individuals. They have a formal semantics, and they are decidable fragments of first-order logic. So they're subsets of first-order logic. First-order logic satisfiability is well known to be undecidable. So that means that a sound, complete, and terminating algorithm is impossible. Description logics, however, provide you a terminating algorithm. Description logics allow one to extract implicit knowledge about concepts and individuals via a reasoning engine from explicit knowledge. Among those reasoning tasks are, for example, subsumption checking to check whether a concept is a subset, in other words, a subclass of another concept, and concept consistency checking to check whether a concept can have instances. So the first is concerned with figuring out, is cat a subclass of animal? And the other one is concerned about, can the class cat have instances in our knowledge base? Now, description logics are well suited to describe a universe of discourse and have been put forward as the foundation of the Web Ontology language. Description logics have been well studied for decades and guarantee certain properties such as terminating algorithms. And they are supported by various tools and libraries, a lot of which have been incorporated in tools that support Web Ontology language ontology engineering, such as Protege. Note, however, that there are different assumptions in description logics in OWL, which we will highlight and emphasize in both lectures. Already said that in description logics, you can describe your universe of discourse in terms of individuals, concepts, and roles. Now, what are those? Individuals corresponds with constants in first-order logics, if you're familiar with first-order logics, and they're also called individuals in the Web Ontology language. And they will be used to represent things, elements of a specific domains, such as Christoph, which can be a person later on, Open Information Systems as a course, Trinity College Dublin as a Dublin. Now, those individuals are things that we can find in real life. And I just said that Christoph is a person, Open Information Systems is a course, Trinity College Dublin is a university. Well, those things will correspond with concepts, and they're called classes in the Web Ontology language and RDFS, and they correspond with unary predicates in first-order logics. So concepts represent sets of individuals that share some properties, such as person, student, course, and even more complex concepts such as professors only teaching grad courses. Now, those individuals play roles upon one another, and those roles are called properties in the Web Ontology language and RDFS, and they correspond with binary predicates in first-order logics. So they allow us to establish binary relations between concepts, and examples include teaches, attends, supervises, and even more complex roles such as teaches and supervises. Now, in description logics, you also have access to a set of constructors to allow us to build complex concept descriptions and complex role descriptions from atomic concept and role descriptions. An example of a complex concept could be student and broke to represent or describe broke students. Description logics are a family of languages, and each language or dialect is named following a naming convention, stating which operators are allowed, and they all start from a base language. The base language is called AL, and that stands for attributive language, and that allows atomic negation, but only on the right-hand side of inclusion equality axioms. For example, we can state that if something is a cat, that something is not a dog. It is atomic because it's related or placed next to a name of a concept, and it can only appear on the right-hand side of inclusion and equality axioms. The base language also provides us concept intersection, allowing us to state that something is part of two concepts, such as student and broke. We have universal restrictions that allows to state things that only play a particular role on other things. So this is the concept denoting things that only have human friends. And then there's a limited existential restriction. It only allows the universal concept. So for instance, we can only declare the things that has a friend. We cannot declare that those friends are human. That is not allowed. The only thing that is allowed is the existential restriction on the universal concept true. Now, additional letters will indicate other extensions. Here's a list of letters commonly used in the naming of description logic languages. And this list will become useful in the next lecture because the different web ontology language flavors have different capabilities, and those capabilities are identified with those letters. The first three letters are FEC. So the F stands for functional properties, and that allows us to state that a property can have at most one value for every subject. We can use this to declare that each person has at most one biological father. The letter E allows us to qualify existential restrictions. So here we have the concept of the things having at least one human friend, which was impossible before. If we were to add complex concept negation, we can put the not symbol in front of complex concept descriptions, such as not, student, and broke. So the letter U stands for concept union, which allows us to describe concepts such as dog or cat, which would have been useful for our name property example a couple of slides prior. The letter H provides us role hierarchies, allowing us to state that husband of is a subproperty of spouse of. The letter R provides us various actions we can declare on roles, such as role inclusion, reflexivity, irreflexivity, and role disjointness, the latter of which an example can be if you're the sister of somebody, then you cannot be the brother of that somebody. Then the letter O provides us nominals. That allows us to use individuals in concept descriptions. An example could be to equate a concept with an exhaustive list of individuals. For instance, with some abuse of notation, we have the cats of Christoph as a concept, and I equate this with Victor, Bettina, and Gaston. The letter I provides us inverse properties, and inverse properties allows us to approach a property from the other way around. For instance, if I have the property has_pet going from person to animal, the inverse of has_pet is the property that goes from animal to people. Inverse properties allows us to relate two roles with one another. So, for instance, we can say that has_pet is equivalent with the inverse of has_owner. And that way, if I state that Christoph has as a pet Victor, then the reasoning engine will infer that Victor has the owner Christoph. The letter N provides us cardinality restrictions that are not qualified. We can state that a happy person is a person that has at least 5 friends, but we cannot state that those friends have to be human. That's why we need qualified. If you need that, you need qualified cardinality restrictions. They allow you to qualify those cardinality constraints. And then you can state that a happy person is a person with at least 5 human friends. Finally, then we have letter D, which is useful for the Web Ontology language. That allows us to use data type properties, data types, and data values in our knowledge base. We know that AL is the base language. If we were to add concept complex negation, we get the dialect ALC, which is a popular description logic dialect. If we were to add transitive roles denoted with R plus to ALC, we obtain the dialect S. Rather than using ALCR plus, ALCR plus gets the shorthand S. Now, the Web Ontology language flavor OWL1DL, which we will be covering in the next lecture, has as an underlying formalism join D. So we have our ALC with transitive roles denoted by S, we have our role hierarchies, we have our nominals, we have our inverse properties, we have our number restrictions that are not qualified, and we have our data types. The underlying formalism of OWL2, the one superseding OWL1, is Schroik D. So here again, we start off with the language S. Instead of H, we have R. So we have our role axioms, which include role hierarchies. We have, again, our nominals. We have our inverse properties. And we have qualified number restrictions instead of the unqualified ones. And we also have our data types. Now, since ALC is equivalent with ALEU, so with qualified existential restrictions and disjunction, we will consider them to. We will also consider these to be part of our language ALC. Why is that? Well, we know that from our logic courses that the union can be rewritten as in function of the conjunction and the negation, the laws of De Morgan. And we can also rewrite our qualified existential restriction in terms of negations and our universal restrictions. So we can say that ALEU can be rewritten as ALC axioms. If we were to create a knowledge base using ALC, where do we start? Well, first we start with the basic vocabulary that consists of 3 disjoint sets. One for concept names, denoted NC, and that includes the universal concept T, also called top, that is the universal true. And we also have our bottom concept, the inverse T, which we will call bottom. Then we have a set for role names, denoted NR, and we have a set of individual names, denoted NI. The recursive definition of an ALC concept description is as follows. If A is an element of NC, then A is an ALC concept description that is atomic. If C and D are ALC concept descriptions, and R is a role name, then the following are ALC concept descriptions. We have the concept conjunction, we have the concept disjunction, we have our concept negation, we have our value restriction, and we have our existential restriction. And see that we already allow qualified existential restrictions, and concept description. Nothing else is an ALC concept description. Note that inverse properties are not part of ALC, but we will cover them in exercises. Before we formalize all the constructors, it might be worthwhile to go over how you can actually read them in a more human readable language. So for the negation, it's pretty straightforward. You can read that as the concept not student. So all the things that are not student. The concept intersection and concept disjunction are also pretty straightforward. Those correspond with the concept, lecturer, and student, and lecturer or student. The universal restriction is a little bit more tricky. You read for all attends.lecture on the left as attends only lectures. So that will be the thing that, if it plays the role of attends, only on things that are of the class lecture. Then for the existential restriction, you read there exists teaches.lecture as teaches some lecture. That corresponds with the concept that must teach at least one thing that is a lecture. You might have already gotten the gist of the meaning of these constructors, but let's go over the meaning here. Negation is to be interpreted as a complement of a set of individual. So here we have not student. So that denotes the things that are not part of the set of students. Conjunction is interpreted as the intersection of sets of individuals. So here we have the intersection of the set of lecturers and the set of students. The disjunction is interpreted as the union of sets of individuals. Similarly, here we have lecturers together with students. The value restriction requires all individuals to belong to the concept associated with the relationship. So here, this denotes the set of things that only attend lectures. The existential restrictions require some individuals to belong to the concept associated with the relationship. So here we have the concept of things that teach at least one lecture. And you might have noticed that I talk about sets, and sets a lot, so that brings us to the semantics of ALC. The semantics is defined by interpretations. What is an interpretation? Well, an interpretation is a pair delta I and I, where delta I stands for the domain, which has to be non-empty, and I is an interpretation function. That interpretation function maps every concept to a subset of our domain, every role to a subset of the Cartesian product of our domain, and every individual to an element of our domain. Looking at the vocabulary and grammar of ALC, here we see below in the table a description of the syntax and their corresponding semantics. We see that the top concept, which denotes everything, is mapped onto our whole domain. The bottom concept, which stands for false, is mapped onto the empty set. Every atomic concept, as shown above, is mapped onto a subset of our domain, and every atomic role is mapped onto a subset of the Cartesian product of our domain. The concept conjunction and disjunction of two concept descriptions are mapped onto the intersection and union of the interpretation of these concepts. And again, you can see that this is a recursive definition. The concept negation or the complement is mapped onto the set minus of our domain and the interpretation of our concept. The semantics of universal and existential restrictions are also mapped on sets, and they're a little bit more tricky to understand. So let's take for all our on C. Now that concept description is mapped onto the set of X, for which X is an element of our domain, and for every Y in our domain, if R the X plays the role of R on Y as an element of the interpretation of Ry, then Y must be an element of the interpretation of the concept C. Similarly, for the concept denoted with an existential restriction, there exists an R on C, well, that concept corresponds with the set of X, for which X is an element of our domain, and there exists a Y, for which Rxy is an element of the interpretation of our role, and Y is an element of the interpretation of the concept C. So far we have seen how we can make concept descriptions, but how can we describe how those concept descriptions relate to one another? For instance, we want to state that a teacher is a type of human, which is a specialization or an inclusion. Or we want to state that human is equivalent to person, which is a concept equivalence. Description logics allow one to state these as axioms about concepts. There are two of them. There's the general concept inclusion, denoted C with a square subset equals D, and the semantics of that is that the interpretation of C must be a subset of the interpretation of D. We also have concept equivalence, denoted C equivalent with D, and the semantics is that the interpretation of C must be equal to the interpretation of D. In other words, both sets must be equal. Now, it's easy to see that C equivalent with D is basically a shorthand for stating both C is included in D and D is included in C. Note that our language, ALC, does not provide role axioms. There are more expressive description logics that do, for instance, to state that child of is equivalent with parent, the inverse of parent of. So far, we've seen how to create concept descriptions and how we can relate concept descriptions. Now, what about a knowledge base? A knowledge base in description logics is a pair TA, where T is a set of terminological axioms, or concept inclusions and concept equivalences, and that set is also called the terminology box or the TBox. Then we have A set of assertional axioms, and that is also called the ABox or the assertion box. And in this lecture, we will be mostly using TBox and ABox because they're just short and easy to say. If you were to compare a knowledge base in description logics with a database, for instance, well, the TBox can be compared with the schema and the ABox can be compared with the data. Here we have an example of a knowledge base. In our TBox, we state that lecturer is defined as a person and not a student, and a student is equivalent with or defined as a person and attending at least one lecture. In our ABox, we put two assertions. I state that Christoph is a lecturer, and I state that Christoph teaches iOS. And do notice that there are roles and concepts that are not included in the TBox, which is fine. The TBox contains a finite set of general concept inclusion and concept equivalences. And I might have said it on the prior slide, but the definition is a concept equality where the left-hand side is atomic. And these are useful to provide symbolic names to complex concept descriptions. Here you can see that I've defined cat person as a person and something that owns at least one cat. What if we cannot define a concept completely? Well, concept inclusion allows us to model the necessary conditions using specialization. For instance, what makes a cat a cat? We might have trouble defining something as follows. A cat is defined as an animal and provide an exhaustive, complete way to describe what a cat is beyond being an animal. If that is impossible, we just provide the necessary conditions for stating that if something is a cat, then it is an animal. So we merely require that all cats are animals. So if something is a cat, then that something is an animal. I claim in no way that this lecture covers everything of description logics. Description logics is a course on its own, a field on its own. My goal is to provide you with the necessary background knowledge and jargon in order to understand web ontology language, ontology engineering later on. I do, however, need to introduce some terminology. So let's start. A generalized terminology in description logics is a TBox where the left-hand side of all axioms are atomic, and each atomic concept only appears once on the left-hand side of an axiom. So for instance, if we were to have foo is in C and foo is in D, well, that is not allowed. We have to rewrite that as foo is in C and D. And I hope you can see why. Now, a regular terminology is a generalized terminology that only contains concept equivalences. So these are not allowed. You have to use these. Now, we've already seen that sometimes it's difficult to write concept definitions if you don't know everything that defines a particular concept. However, there is a trick. You can create a generalized terminology. You can transform a generalized terminology T into a regular terminology by rewriting it using a little trick. Let's take the example from before. We have that a cat is an animal. Now, if we were to transform that into a concept equivalence, then we will rewrite it as a cat is defined as cat prime an animal, where cat prime is an artificial concept that we introduce that represents the qualities that distinguish a cat from other animals, even though we do not know what they are. I admit this is a trick, but this allows us to rewrite our generalized terminology in a regular terminology to facilitate some of the reasoning tasks by inference engines. For this lecture, however, that's not really that important. Now for the ABox. The ABox is a set of assertions, and those assertions describe the facts specific to an application domain. Now, you can have the same TBox describing cats, people, and their ownership, but the assertions might be different depending on the situation. My ABox is likely different than that of another cat owner. Here I have some facts. I state that Victor is a cat, Christoph is a person, and Christoph owns Victor. Now, how do you interpret that? Well, given an interpretation I, we say that a concept assertion CA is satisfied by that interpretation I if and only if the interpretation of A is an element of the interpretation of the concept. Similarly, if we have a binary predicate asserted in our ABox, RAB, well, RAB is said to be satisfied by the interpretation I if and only if the pair, the tuple, consisting of the interpretation of A and the interpretation of B is an element of the interpretation of the role R. And we also say that an ABox is said to be satisfied with respect to an interpretation I if every assertion in A is satisfied, which is written as I models A. There are two common assumptions for the ABox in description logics, and this is important to understand for this lecture and the lecture on web ontology languages. The first one is the unique name assumption. That states that individual names in the interpretation are distinct. In other words, if you have two individual names, their interpretation will refer to different elements in the domain. So the interpretation of A is different from the interpretation of B. The unique name assumption is usually adopted in description logics, but not on the semantic web, and we will later on describe or explain why. The second assumption is the open world assumption. The open world assumption presumes that the information in the ABox is incomplete. So assertions in the ABox represent statements that are true in all models, but Not that all unknown informations not occurring in the models are not true. Sounds complicated, but it boils down to what is not known is not necessarily false. Before I can continue with reasoning, it is important that I describe two things. First, a description of the relationship between description logics and first-order logics, and then the differences between databases and ontologies. For the first, we will see how we transform formulas in description logics into formulas in first-order logics, and this may be handy if you have seen semantic tableaus for first-order logics in your undergrad. This part may be skipped if you merely want to get the gist of description logics. For the second part, we will try to understand via comparing the differences, the more quirkier aspects of description logics and its behavior when used on the semantic web. So the relationship with first-order logic. We've already stated that description logics are decidable fragments of first-order logic, and concept descriptions correspond to first-order logics with one free variable. Those free variables will be bound when used in a concept inclusion or an equivalence statement. Translating assertions in a description logic into first-order logic formulas are provided by a paper by Frans Bade and others. And the translation of concept description C into a full formula with one free variable is given by the transformation function tau x, with x being the variable that we will be using, as follows. An atomic concept is transformed into a unary predicate. The concept intersection is transformed into the conjunction of the transformation of that concept description C and the concept description D. Similarly, the concept disjunction is transformed into the disjunction of the transformation of the concept description C and the transformation of the concept description D. The concept negation is transformed as the negation of the transformation of the concept description C. And then we have our universal and existential restrictions. So the universal restriction for all R on C is translated as being a for all Y. If Rx on Y is true, then that implies, and then we have the transformation of our concept C using a different variable. The same for the existential one, but here we use the existential quantifier and it has to be a conjunction. And you can see that the variables x remains unbound. Now, if we have a TBox T with concept inclusions, and remember that we can rewrite our concept equivalences as two concept inclusions, the translation tau of our TBox is given by the conjunction of all our concept inclusions in T, and we will just surround the implication between the transformation of our concept description C and our concept description D, the transformation thereof, around a quantor with variable x. Let's provide an example of this transformation. Assume that in our TBox we have one concept inclusion, which is a broke student is a student and not rich. We will now transform this concept inclusion with these rules. I will be using the letters B, S, and R just to make it easier for myself. So first we do apply this rule. We only have one, so we have the universal quantor for all x, and the concept inclusion will be transformed inside that one. We have the concept inclusion becomes a implication, and the first operand typos there, sorry. The first operand is a transformation of broke student. We know that broke student is a atomic concept, so that will be transformed as follows, Bx. The consequent of the implication is the concept description student and not rich. This is a concept intersection and has to be transformed as follows. It will be transformed into a conjunction, and then both student and not rich will be transformed as operands of that conjunction. Student is a atomic concept, so that's pretty easy. We have Sx, and the second operand is not rich, that is a concept negation, so we provide the negation here, and rich is a atomic concept again, so we have not Rx. So we have transformed this formula. Second example with a existential restriction. Assume we have a terminology box with only one concept inclusion being a happy person is a person and something that has at least one friend that is a person. How do we translate this? Well, first we avail of this rule. We choose a variable. We start with x, and this results with a quantor for all x for this implication. The antecedent of the implication is a atomic concept that is pretty straightforward to translate. So happy person becomes a unary predicate. The consequent of the implication is a complex concept description, person, and has some friend that is a person. So it is a conjunction. And the first part of the conjunction, the first operand is a atomic concept, which is straightforward to translate, Px. The second part is a existential restriction, for which we need to avail of this rule. Okay, so the second operand becomes a there exists, and now we need to choose a variable that is different from x. We will choose y, and then we just translate the remainder. So has friend, there exists a y, age, x, y, and person is an atomic concept, so becomes a unary predicate. But here we have to use y. What about the differences between databases and ontologies? Well, in a database, we adopt the closed world assumption. Missing information is treated as false. In a database, we do adhere to the unique name assumption. Each individual has a single unique name. In a database, the schema contains constraints that define legal database populations. In other words, the schema is used to figure out whether a database state is legal or not. Now for ontologies, in ontologies, the closed world assumption is not adopted, but the open world assumption is adopted. Missing information is treated as unknown, not as false. Description logics, and the ones that we cover in this lecture, usually adopt a unique name assumption. Each individual has a single unique name. In the Web Ontology language, the unique name assumption is not adopted. Each individual can have multiple names, and we will talk later on why. In ontologies, the axioms are used not to define legal states of knowledge bases, but to infer implicit information from explicit information. And that includes whether or not a knowledge base contains a contradiction. Now, why would the Web Ontology language and the semantic web not adopt the unique name assumption? Well, it's pretty straightforward and simple. On the web, things can have multiple identifiers. I, for instance, have several URIs, one from Facebook, LinkedIn, Twitter, and so forth. So I do have multiple names on the semantic web. Assume the following facts are in our knowledge base or database. I have 3 cats, Victor, Bettina, and Gaston, and I state that Christoph has as a pet Victor and Christoph has as a pet Bettina. Now I ask the question, is Gaston Christoph's pet? From a database perspective, the answer is no. From an ontology perspective, however, because of the open world assumption, the answer is we do not know. Why do we not know? It was not explicitly stated that Gaston was not Christoph's pet. Here's another example. We have the same facts in our knowledge base or database, but I answer now a different question. I try to answer a different question. How many pets does Christoph have? From a database perspective, the answer is 2. Why? Well, there's only 2 facts about me owning a pet, and the labels, because of the unique name assumption, are referring to different things. For an ontology with the unique name assumption, the answer is at least 2. We know that Christoph has a relation, has pet, with 2 named individuals, and those names must refer to different things in the domain because of the unique name assumption. But because of the open world assumption, we do not know, we cannot be certain that Christoph does not have more cats. Now, in an ontology without a unique name assumption, things become a little bit more interesting. In an ontology without a unique name assumption, the answer is at least 1. Why? Well, it is possible that the labels Victor and Bettina refer to the same thing in the domain. It was not explicitly stated that they refer to different things. So hopefully you now start to see how what the implications of the open world, closed world assumption and the unique name assumption are. I add a fact to our knowledge base. I state that Victor and Bettina are different, and there's a predicate for that in OWL, which we will cover in the next lecture. If we state that Victor and Bettina are different, what would be the answers from a database perspective? It would still be 2 for a database, but for a ontology with the unique name assumption, it now becomes at least 2. And for the ontology without a unique name assumption, it also becomes at least 2, because now that ontology knows that Victor and Bettina refers to different things in the domain. Now let's another fact to our knowledge base. Now I add that Christoph is an instance of the concept of the things that the relation has pet only on the class that contains Victor and Bettina. Here I declare a concept description as an exhaustive list of individuals, which is possible with the nominal extension and available in the Web Ontology language with the construct all values from. So I state that Christoph has as pet all values from Victor and Bettina. Now, how many pets does Christoph have? Well, from a database perspective, the answer remains 2. But from an ontology perspective, with and without the unique name assumption, instead of at least 2, we now know it's exactly 2, because Christoph only plays a role of having a pet on these 2 cats. So now you see that if we want to be precise or as accurate as possible, we need to provide as much information as possible in our knowledge base in order to come up with accurate answers. Beginning of this lecture, we've seen that reasoning allows us to ensure that a knowledge base is meaningful, correct, and minimally redundant. Reasoning also allows us to answer queries over ontology classes and instances. One important reasoning task is to figure out whether our knowledge base is satisfiable, which means that it can happen. It doesn't contain any contradictions. Now, given a knowledge base K with TBox T and ABox A, knowledge base K is said to be satisfied by an interpretation I if and only if that interpretation I satisfies both T and A. In other words, it satisfies all the axioms in T and it satisfies all the assertions in A. A knowledge base K is consistent if and only if there exists a model for K. Basically boils down to K can happen. And testing the satisfiability of a knowledge base can be done by checking whether contradictions or false cannot be inferred from that knowledge base. Let's illustrate some of the reasoning services with the knowledge base on the left. In that knowledge base, I have a TBox in which I have defined cat person as being a person and something owning a cat. A cat is an animal, and a dog person is defined as being a person that is and not a cat person. In my ABox, I have declared that Christoph is a person, Victor is a cat, and Christoph owns Victor. The first reasoning service we will cover is concept satisfiability. That means that a concept description can have instances. In other words, we shouldn't be able to derive that the concept is a subset of the bottom class, the empty concept. Let's see whether this concept description, cat person and not person, is satisfiable. We will see that it is not. Why? A cat person is defined as being a person and something owning a cat. Therefore, this complex concept description requires that thing to be a person and not a person at the same time, which is a contradiction. The second reasoning service is subsumption checking, checking whether a concept is included in another concept. Let's check whether cat person is a person. We will see that this is true. Why? A cat person is defined as being a person and something owning a cat. Therefore, a cat person is a person. An important reasoning service is knowledge-based satisfiability checking, where we will actually check whether our knowledge base contains a contradiction taking into account the individuals in our ABox and our TBox. In other words, our knowledge base shouldn't allow us to derive the bottom concept. Now, our current knowledge base is satisfiable, but what if I were to include the following assertion? Not cat person Christoph. Well, this would lead to a contradiction. Why? We know that Christoph is a person and Christoph owns a cat. Therefore, because of this definition, Christoph is inferred to be a cat person, and together with not cat person Christoph, we have a contradiction, and the knowledge base is not satisfiable. Another reasoning service is instance checking, checking whether an individual belongs to a class. An example here is asking whether Victor is a cat. In our knowledge base, we can derive that immediately from the ABox, but it can also be inferred indirectly, inferred from actually finding implicit information from the explicit information in our knowledge base. A last reasoning service we will cover in this slide is retrieval. We will query things and find instances that or tuples that adhere to that query. Here, I query animals, and I ask for all the individuals that are animals in our knowledge base. Remember, Victor is declared as being a cat, but because Victor is a cat and all cats are animals, Victor is therefore also an animal. Therefore, Victor will appear in our result set. How can we reason? Well, most reasoners are based on Tableau calculi and the Tableau algorithm, also known as semantic Tableau, to solve the satisfiability problem or other reasoning tasks. Why the Tableau algorithm? Well, the Tableau algorithm is sound, which means that everything that is inferred is true, complete, which means that everything that is true can be inferred, and it is, unlike first-order logics, for description logics, it is terminating. Now, interesting is that a lot of reasoning services or reasoning tasks can be transformed into other reasoning tasks, allowing us to avail of the Tableau algorithm. Here we have 5 reasoning tasks: equivalence, checking, subsumption checking, satisfiability checking, consistency checking, and instance checking. And some of these tasks can be reduced or rewritten into other tasks. We will not cover all of them, just a couple. For instance, checking whether C and D are equivalent in a knowledge base can be reduced to checking whether C is included in D in that knowledge base and D is included in C in that knowledge base, covering this arrow. Similarly, we can check whether C is included in D by checking whether C is equivalent with C intersecting D as an equivalence check. We can also check whether C is included in D, by checking whether C intersection not D is unsatisfiable with respect to that knowledge base. So we reduce subsumption checking into satisfiability checking. And finally, one that I find particularly fun to do is checking whether A is an instance of C by reducing instance checking to consistency checking. For instance, if we want to check whether Victor is a cat, we will reduce it to a consistency check by adding Victor is not a cat into the assertion box, and then apply the consistency check algorithm. And if there's a contradiction, we know that Victor must be a cat. In other words, if not Victor is a cat leads to a contradiction, we know that Victor is a cat. It's related to the reductio ad absurdum. The Tableau algorithm for ABox consistency needs individuals. It needs an ABox, and it will try to generate a finite model for the input ABox A0. How? Well, it will apply Tableau rules on the ABox. Those transformation rules may result in new ABoxes that have to be inspected. When does the algorithm terminate? When no more rules can be applied to any ABox, and then you have answers. Either the knowledge base or the ABox and the knowledge base is consistent if there is at least one open and complete ABox. Open means that there are no obvious contradictions of the form C and not CA. And it is complete, which means that no more rules can be applied to that ABox. The answer is inconsistent if all ABoxes are closed, which means that all ABoxes contain obvious contradictions. You can visualize those ABoxes and the ABoxes that are created as a tree. And I will try to exemplify that with the figures below. So assume we have an ABox A0, and we apply transformation rules until either an ABox contains an obvious contradiction or an ABox is open and complete. So red circles will denote an ABox with an obvious contradiction. Green circles will indicate an ABox that is open and complete. Now, okay, the question that I ask myself is, are the following knowledge bases consistent? Well, here I have an ABox A0, and I apply some sort of rule, and it turns out that it resulted in A0 and a new ABox. Then I applied a rule on A1, and I have an obvious contradiction, so this one is closed. On A0, I apply another rule, and which results also in a new ABox, A2, and this one is complete and does not contain an obvious contradiction, which is great. The other one, however, contains a contradiction and therefore is closed. Now, is this knowledge base consistent? The answer is yes, because there's at least one open and complete ABox. So that means there's a model, and therefore the knowledge base is consistent. Here we have a similar scenario, but with two open and complete ABoxes, and the answer is the same. Why? Well, a knowledge base is considered consistent if there's at least one open and complete ABox. And then on the right, we have the situation where all of them are containing obvious contradictions. That means that there is no open and complete ABox. All ABoxes contain contradictions, and therefore there is no model for that knowledge base, and that knowledge base is inconsistent. What if we only have a TBox, only a schema, but no individuals? Well, before I explain how we can tackle that problem, we have to remember that we only deal with generalized terminologies. That means the left-hand side of all axioms are atomic, and each atomic concept only appears once on the left-hand side of an axiom. We will also avoid cyclic terminologies, which correspond roughly with recursive definitions, either directly or indirectly, for this lecture. This allows us to reduce TBox reasoning to ABox reasoning. And again, I refer to this paper for more information. Now, as for the what if we only have a TBox and we want to test whether a concept can have instances? In other words, the concept is satisfiable. Let's take our TBox from the previous example, where I define cat person being a person and something owning a cat is an animal, and a dog person is defined as being a person and not a cat person. Now I ask the question, can the concept cat have instances? In order to test the satisfiability of that concept, in this case cat, the algorithm starts with an ABox containing a individual name, random one that you choose, and you state that that individual is of that concept, in this case cat, and apply transformation rules to the ABox until no more rules apply. Again, if one of the complete ABoxes obtained this way does not contain a contradiction and is complete, then it is consistent and therefore C is satisfiable. On the other hand, if all the ABoxes obtained this way do contain a contradiction, then A0 is consistent and thus the concept is not satisfiable. Satisfiability checking allows us to check whether there's a model. What is a model? A model is an interpretation that satisfies either the knowledge base, the terminology box, or the ABox. An interpretation I satisfies a TBox, T, if it satisfies every axiom in T. In other words, for every C included in D, you have that the interpretation of C is a subset of the interpretation of D, using a non-empty domain. An interpretation I satisfies an ABox A if it satisfies every assertion in A. In other words, for every CA in A, the interpretation of A is an element of the interpretation of C, and therefore also in the interpretation domain. And for every role AB, or role RAB in A, the tuple containing the interpretation of A and the interpretation of B is an element of the interpretation of the role R. An interpretation I satisfies a knowledge base if it satisfies both the TBox and the ABox. A knowledge base is said to be satisfiable if there exists at least one non-empty interpretation and non-empty domain satisfying that knowledge base. Note, it may very well be that your knowledge base is satisfiable, but concepts in the knowledge base are not. Concept satisfiability checking is a separate task. We will cover such an example later on. Negation normal forms. Before we start applying the Tableau algorithm, we normalize all concept descriptions into their negation normal form, or NNF. The goal of NNFs is to rewrite and push negations in formulas so that they only occur in front of their atomic concept. This is achieved with the following rewriting rules. For instance, a negation in front of a concept intersection is rewritten as the disjunction of the negated operands of that intersection. For the existential restriction, a negated existential restriction is transformed into a universal restriction where the negation is pushed down to the concept description of that restriction. Finally, double negations are just removed. Once that is done, we can apply the Tableau algorithm. But what about concept equivalence and concept inclusion? Well, first, remember that concept equivalence can be rewritten as two concept inclusions. Also, because ALC is equivalent with ALU, we are able to rewrite concept inclusion C implies D as not C or D. Why is that? Well, that's because this is equivalent. A implies B is equivalent with not A or B in logics. This allows us to only avail of the rules for disjunction, intersection, the universal and existential restriction. But we will cover other rules as well for inclusion and concept equivalence. Transformation rules of the Tableau algorithm. Let's start with the intersection rule. The intersection rule states that if an assertion box contains X is a C and D, but it does not contain both X is a C and X is a D, then we can add to the assertion box X is a C and X is a D. For example, if our assertion box contains that Victor is a cat and is black, and the assertion box does not contain both Victor is a cat and Victor is black, we can add to our assertion box that Victor is a cat and Victor is black. The concept disjunction rule is a bit trickier because it results in a new assertion box. Let's for instance state that our assertion box A contains X is a C or a D, but neither X is a C nor X is a D is in the assertion box. Then we can add Cx to A and we can add Dx to another assertion box. For example, assuming we have a set of formulas sigma in our assertion box, a set of assertions rather, and we have that Victor is either a cat or a dog, and nor Victor is a cat nor or Victor is a dog is in the assertion box, then we can add Victor is a cat in 1, and we copy paste the old one here, all the assertions included, and then add the other assertion, Victor is a dog. The rule for existential restrictions. That rule states if an assertion box contains that X is an element of the things that play some role R on C, but there's no individual C such that C is a C and X plays a role R on Z in A, then for some individual Y, where that individual name does not occur in A, you can include into the assertion box that Y is a C and X plays a role of R on Y. For example, let's say that I am the element of the concept of having some cat. Has some cat. And let's suppose I also play the role of has on something else, Fifi, but I do not declare Fifi to be a cat. Then, because there's no individual Z, such that Z is a cat and Z is being played the role upon by X or myself, the role has, I can introduce a new individual by choosing an individual name not occurring in A and insert both or assert both that that thing is a cat and I play the role of having that thing. Let's choose the individual named Foo and I introduce that Foo is a cat and I have Foo. The universal restriction the rule, therefore, states that if A contains X is an element of Ring only C, and it does contain X plays the role of R on Y, but it does not contain that Y is a C, then you can include that y is a c is in the assertion box. The universal restriction the rule, therefore, states that if A contains X is an element of Ring only C, and it does contain X plays the role of R on Y, but it does not contain that Y is a C, then you can include that Y is a C is in the assertion box. Let's reuse our example with Fifi. I state that I'm an element of, for all has cat, and remember, this universal restriction means that those things only play the role of has on cat. So has only cat. I state that Christoph has Fifi. Now, I know that Christoph is part of that concept and Christoph has Fifi. Because our assertion box does not contain that Fifi is a cat, we can now add to our assertion box that Fifi is a cat. Why? Because Christoph only plays the role of having on cats. So we now add cat Fifi. So Fifi is a cat. So for example, assuming that we have two individuals, we have Victor and we have Gaston, and in our TBox, we have two concept inclusions. We have cat as an animal, and we have car is a vehicle. Because I know that neither Victor nor Gaston appears with not cat or animal and not car or vehicle as assertions in the ABox, I can include those. So we will have not cat or animal Gaston, not cat or animal Victor, not car or vehicle Gaston, and not car or vehicle Victor. And that's how we emulate the concept inclusions of our terminology box. Yes, our knowledge base can explode because of that, but those are considerations that are investigated in the description logics community, but for our purposes, this suffices. For the equivalence transformation rules, we assume that we are only dealing with acyclic terminologies, so no recursive definitions, and that the left-hand side of these axioms only contain atomic concepts. There are two of them, and they're pretty straightforward, assuming that I declare a pet to be defined as cats or dogs. So in my universe of discourse, I only have cats or dogs. Now, if I were to state that foo is a pet, and it is not asserted in the knowledge base that foo is a cat or a dog, then I can include foo as being an instance of that concept in the knowledge base. So then I will end up with cat or dog foo. Similarly, for the negation, if I state that Joe is not a pet, then I know that Joe, and it is not stated or in the assertion box that Joe is not a cat or dog, then I can include that Joe is not a cat or dog. So not, oops, cat or dog. Joe. And that's it for the transformation rules. It has taken us some time, but I promise you things will become a lot more tangible with a couple of examples. This example, I want to test whether the following concept, has friend some person, is satisfiable. First, we need to check whether the concept description is in negation normal form. The answer is yes. Then we will prepare the ABox A0 and instantiate the concept with an individual x, and then we will apply the transformation rules. So here we have our ABox with our individual x. There are a couple of the transformation rule we can apply is the existential restriction rule, which results in two more assertions in the ABox, has friend xy and person y. Are there any other rules that I can apply? No, we're done. Are there any obvious contradictions? No, there are none. That means that all ABoxes are open and complete, and the concept is thus satisfiable. Happy days. Second example, a little bit more challenging. The following concept description. Not attend some course and not attends only not courses is satisfiable. Well, first of all, the concept is not in negation normal form because because most of the negation symbols are not in front of atomic concepts. So we apply a couple of rules. We see that I push this negation symbol here, which results in a change of the quantar. Similarly, I move this one over there, it changes the quantar, and now I have double negation here, which I eliminate here. We then prepare the ABox A0 and instantiate the concept with individual x, and then we apply the transformation rules. So here we have our ABox, and x is an instance of attending only not courses and attending some course. I hope you can see intuitively this will lead to a contradiction, but we will apply the Tableau algorithm anyway. First, we apply the intersection rule, and we see that this results in two new assertions. X is an instance of attending only not courses, and X is an instance of attending some course. Then we will apply the existential restriction rule, which results in two assertions. X is attending Y, and Y is a course. Then we will apply the universal restriction rule, which results in Y being a not course. Why? Well, X is attending Y, and Y is not an instance of not course. Therefore, Y being an instance of not course is added to the knowledge base, or the assertion box here, rather, and this is an obvious contradiction. Because there's an obvious contradiction, this assertion box is closed. Now, even though this ABox is complete, we could terminate upon finding an obvious contradiction, but in this case, all ABoxes contain contradictions, therefore, the concept is not satisfiable. As a third example, we will check whether a knowledge base is satisfiable. A forewarning, the concept lecturer is not satisfiable in this example. We are, however, going to check knowledge base satisfiability, which means is there a non-empty interpretation satisfying all axioms in the terminology box and the assertion box? And the answer will be yes. Concept satisfiability is a different question. Now, in our example, in our terminology box, we have that a professor is not a student, and a lecturer is a professor and a student. I also declared Christoph as being an instance of professor in the assertion box. Notice that this is a silly example, it's just to illustrate Tableau reasoning. The first step is processing the inclusion rule to all individuals. I did abbreviate all the symbols to make my life easier. That means that I have declared Christoph as being an instance of not professor or not student, and Christoph is an instance of not lecturer or professor and student. We've already done the inclusion transformation rule. Let's do the rest. So our ABox currently contains 3 assertions. Applying the disjunction rule results in a new ABox, A1. In one ABox, I add, because I've been transforming this assertion, I have the introduction of C is a not P. This leads to an obvious contradiction that you can see here, so this one closes. In the other ABox, I have introduced, or I had to introduce, C as a not S. This one is open, but not yet complete because I can still process this assertion. In doing so, I have 2 assertion boxes, my A1 and my A2, because again, this is a disjunction. So I have to create a new assertion box. The first one, I have introduced C is a not L, and the other one, I have introduced C is a P and S. Okay, this seems to be open and complete. The other one is not complete yet, so I apply the conjunction rule, and I notice, because I added both C is a P and C is an S, that I have an obvious contradiction in S. C is both a not S and an S at the same time, so this one closes as well. Because I have an open and complete ABox, this is thus an interpretation for the knowledge base. There can be a model. The knowledge base is thus satisfiable. Now, as for the final example, I will reuse the same TBox, but I ask myself the question, is the concept lecturer satisfiable? Well, the algorithm starts, as with the first 2 examples, with an ABox A0, and I've chosen the individual name X to instantiate lecturer. We will apply the transformation rules to the ABox until no more rules apply. Again, I apply the inclusion rule to all the individuals, which you can see here. And then on the next slide, I will apply all the other transformation rules. We've already applied the inclusion transformation rule. Now let's apply the rest of the rules. Because I know that X is a lecturer, I, as a human, can come up with strategies or heuristics to try to find those contradictions as soon as possible. And I know that I won't be finding them here, but I might be finding them there because I see an L there. Some of these heuristics have been implemented in Tableau algorithms to render the process more efficient. So I apply the disjunction rule, and that leads us to 2 ABoxes. In the first one, I introduce X is a not L, and that leads to an obvious contradiction, so this one is closed. In the other ABox, however, I have included that X is a P and S. That ABox is not yet complete and is still open, so we have to, and it doesn't contain any obvious contradictions, so we still have to process some of the assertions. The next assertion that I will process is the conjunction of P and S. So the concept intersection. I know that X is a P and S, so therefore X is a P and X is an S. Again, no obvious contradiction, so we have to continue. The reason why I chose the concept intersection over the concept union is that I know that this one doesn't generate a new ABox. I try to keep the number of ABoxes to a minimum. Then we process the disjunction that we have here. Great. In one of the ABoxes, I have introduced X is a not P, leading to an obvious contradiction with X is a P, so this one is closed. In the other ABox, similarly, I have introduced that X is a not S, which is an obvious contradiction with X being an S here, so this one is closed as well. So the existence of a lecturer leads to contradictions in all ABoxes. Therefore, the concept lecturer is not satisfiable. I hope the examples made description logics a lot more tangible. Now, to conclude, description logics provide the foundation for the Web Ontology language, which is why we covered description logics in this lecture. We introduced various important concepts, not to be confused with description logics concepts, that we will mention in the next lecture. We've only scratched the surface of description logics, so if you're interested in the topic, I suggest starting with the references included in this presentation. That said, here are the references used throughout the lecture, and I look forward to you attending the lecture on Web Ontology Language.